Hello everyone, I hope you all are having a great time. In this video, we are going to solve the problem 3 from chapter 5 of solid state physics by Kittel. The chapter name is phonon 2, okay, related to the thermal properties of materials. And let's see the problem statement and we will dive into the solution directly to save the time because maybe the problem gets lengthy. We don't know. Okay, in part A, this is about 0 point lattice displacement and strain. Wherever you see the 0 point word, it refers to the minimum possible value that the system can have corresponding to a particular property. For example, if we consider energy, then 0 point energy refers to the minimum possible energy that the system can have. And similarly, if we consider lattice displacements and strain in under thermal properties, then it refers to the values of lattice displacements and strains at absolute zero temperature, and so on. Okay, so I hope it's clear to you people, since they are thermal properties and their values depends upon temperature. So yes, and in case of harmonic oscillator, for example, and if its energy is expressed in terms of a quantum number n, then the 0 point energy refers to the energy corresponding to n equals to 0. Okay, because n is equals to 0 is the minimum possible quantum number and it refers to the minimum possible energy that the harmonic oscillator can have. So the situation at absolute 0 is called as the 0 point. Okay, and here we'll be finding out the expressions for lattice displacement and strain at absolute 0, which we are calling as 0 point lattice displacement and strain. Okay, in part A, they are saying in the Debye approximation, we'll be using the Debye approximation, show that the mean square displacement of an atom at absolute 0 is angular brackets are showing the mean thing in symbol form. Okay, for example, we show integration by this sign. All right, and similarly we are showing the mean symbolically by this sign, and r has square. R is the displacement and here is the square, and this shows the mean. So this is the mean square displacement of an atom, and we have to prove that at absolute 0 this is equals to this expression particularly, which is 3h cut omega d square. Here omega d is the Debye frequency, okay, divided by 8 pi square rho v cube. Here rho is the density and v is the speed of sound. All right, or velocity of sound. We are talking about sound here because we are talking about lattice vibrations, we are talking about phonons here. So yes, here v is the speed of sound. And start from the result 4.29 summed over the independent lattice modes. They have actually shown you the result to start with. Okay, we have to start with this result, we have to solve this summation, and we'll prove that this summation will result into this expression. Okay, they have already given the result to start with, and we have to proceed from this result onwards, and we have to prove that this is equals to this. Okay, they have actually given us the a formula to start with. Okay, we have included a factor of 1/2 to go from a mean square amplitude to a mean square displacement. This is an extra information. In part B, in part A, we have to simply prove that this expression results into this expression. Okay, and this expression is what? It's actually the mean square displacement of an atom at absolute 0 under Debye approximation. And in part B, we have to show that this summation, which is summation inverse of omega, which actually appears in this formula, and hence this, because here you can see that the value of the mean square displacement directly depends upon this summation. Okay, so the way this summation behaves is the way this thing will behave too. Okay, so their behavior will be similar because they are directly related with each other. So summation omega inverse and mean square displacement diverge for a one-dimensional lattice. We have to show that for a one-dimensional lattice this summation diverges. Okay, or the mean square displacement of an atom diverges if we consider a one-dimensional lattice, and diverges means the result becomes infinite when we solve it. But the mean square strain is finite, it doesn't diverge, so we will consider this result, which is the mean square strain, Okay, they have already shown us the result to start with here too. This is the mean square strain, and we have to show that it is equals to this one thing for a line of an atom each of mass capital M, counting longitudinal modes only. Okay, we'll talk about what kind of modes are possible in the first part, and you will see how it is to deal with when we are taking the longitudinal modes only. Okay, the divergence of r square is not significant for any physical measurement, so we'll solve the problem. So let's start with the part A, and I'll write this result. Okay, and I'll write this one result too that we have to get at the end. Okay, it will help us to do the things accordingly. So let me solve the part A first. We have to prove that in part A, the mean square displacement at absolute 0 is equals to this expression. Okay, this is something that we have to prove. Okay, let us call it as equation number 1, and we are given with this expression that we have to solve and prove that it's equals to this expression. V, small v is the speed of sound, rho is the density, omega d is the Debye frequency, and here v is the volume, rho is density, h cut is Planck's constant divided by 2 pi, and this is a summation term over omega inverse. All right, and what's other than that, Debye approximation simply means that this expression holds, which means that the speed of sound is constant, or the speed is similar for all independent modes of vibration that a lattice has. For example, we have 3 independent modes of vibration. One is longitudinal and the other 2 are transverse. Okay, in Debye approximation, the speed of sound is independent of any mode, for example longitudinal or transverse, and in Debye approximation we assume that the speed of wave propagation along the in longitudinal mode is equal to the speed of wave propagation in transverse mode. Okay, so this is the approximation that we'll use, but that's just approximation, was generally true that these two speeds are not equal. Okay, and they appear normally in this form. Let me show you people in this form. Okay, this is the speed in longitudinal mode, and this is the speed in the transverse mode. Okay, since there are 2 of the transverse mode, that is why we have 2 over vt cube and 1 over v1 cube, vl cube, actually, because there is only 1 longitudinal mode and 2 transverse mode, and there are actually 3 modes that are available in a lattice. Okay, so in Debye approximation we take all vt equals v1, and actually what we get as the net result is 3 over v cube, that we just simply plug in the density of states formula and proceed further on. So this one fact will appear in density of states formula, and let's proceed. Now we have to solve this summation, and this summation can be written in terms of integral. This is something that you will commonly see in many problems. Here we have 1 over omega. Okay, omega inverse can be written as 1 over omega, which will be multiplied by a weight function, which is actually the density of states. Okay, now density of states multiplying a function by a weight function, which is here a density of state, makes sure that the summation or all of these things has been done over the available states, because as we define density of states, they are not all of the states that are available. Okay, there are only finite number of states that are available to the atoms to occupy, and none other than that will be available. So we have to make sure that the summation or everything has to be done keeping in mind the density of states restriction, and for that purpose we are multiplying that function we are wishing to integrate with the weight function, which is density of states, and we have to sum it from 0, which is the lowest omega, which is allowed to the maximum omega allowed, which is Debye frequency. Okay, Debye frequency is the maximum frequency in which the lattice can vibrate, and it cannot exceed that limit. Okay, because of some normalization conditions, okay, that are implemented on the lattice. So we have this thing now. Let us call this equation as equation number 2, because we need to put the value of d of omega right here in order to solve this integral. And for that purpose, here we'll be dealing with a 3D lattice. Okay, that is why we will be using the formula of density of states for a 3D lattice. And we are considering here all of the independent lattice modes, which means we are considering longitudinal mode and two of the transverse mode also. Okay, in some books we are required to consider only one mode, and for those we'll be using another formula for d of omega, while for the case when we are dealing with all of the independent modes, then we have to multiply the formula for a single mode by 3 simply. Let me do it for you. We know that density of states is given by density of states in 3D is given by d of omega is equals to v naught omega square over 2 pi square v cube. Okay, this is the expression of density of states in terms of omega. Okay, normally we have derived it in terms of k, okay, which appears to be like that, but sometimes we need to convert the main variable from, let's say, from k to omega, from k to e, and so on. So there is a simple transformation equation that you can use to do that. Okay, let me show you that transformation equation, and it will help you to get to any variable. For example, density of states in k variable dk, okay, differential should be equals to density of state in d of omega space times the d omega. Now if we want to find out density of state in omega space, then what we have to do is to do this. Okay, this cancels out and gives you one result. So d of omega will be equals to d of k times differential of k with respect to omega. Okay, this is the transformation equation that you can use. For example, here d of k that we had is this one, and as we were considering the Debye approximation where we had omega is equals to vk, okay, and k could be equals to omega by v equals k. Okay, and if you want to find out dk by d omega, which means here we have k equals omega over k, omega over v, we can write it like that, taking derivative with respect to omega on both sides, d by d omega on both sides. So it's d by d omega of k, d by d omega on omega over v. As in Debye approximation, v is constant, okay, which is the speed of sound. So we got d omega by d omega, and 1 over v into 1 over v. So dk by d omega comes out to be 1 over omega. Now let us put all of these values right here. Okay, that is equals to d of k dk by d omega. The value of d of k is v naught k square over 2 pi square, dk by d omega is 1 over it. Now here it is k, here also we have to remove it and convert it into omega, and we can do it by putting the value of this k right here. K is omega by v, and since it's k square will be simply equal to omega square by v square. So v naught by 2 pi square, k square will be equals to omega square over v square, 1 over v, here v, and this will become 2 pi square v cube. Okay, so density of states formula will become this in omega space. Okay, we have successfully converted into omega space, and if you want to convert it into a energy space, for example, you can do the similar thing. Okay, depending upon which conversion you want to attain. Okay, this is the simplest conversion. All right, so this is a side information that I gave you people. So this is the expression that we will be using now. This is the density of states for a single mode, but we have to consider all of the independent lattice modes, and for that we'll multiply this density of states formula for a single mode by 3 in order to get the density of states formula for all uh, independent states. Okay, I hope you got the point that this formula without 3 is this one thing is the density of states for a single mode, and if you have to find out the total density of states for all the independent states, which includes one longitudinal state and two transverse states, which adds up to give us 3. Okay, there are actually 3 lattice modes in which the vibration can be done. Okay, they are the 3 independent lattice modes, so we have to multiply this formula by 3 in order to get the total density of states. So now we are going to put this expression into expression number 2, and what you will get is h cut over 2 rho v and integration from 0 to omega d 1 over omega density of states formula, which is 3 v omega square over 2 pi square v cube and d of omega as it is. Now all of the constant quantities will be taken out because the integral is on omega, so other than omega terms, all of the other terms will be taken as constant, and we'll take them out of the integral. 3v over 2 pi square v cube, this v is speed and this v is volume, and omega square over omega d omega, 1 omega gets cancelled and we have 1 omega in the numerator, 2 rho, this volume and this volume cancels out. Okay, this 3 will come here. We have 2 pi square v cube, 2 into 2 is 4. Okay, this is 4 now, 4 rho pi square v cube, and we have 0 to omega d omega. Now let us solve this integration, and we'll get integration of omega, as you know this integration to be x square by 2. Similarly, we'll write omega square by 2 from 0 to omega d, 3h cut over 4 2s are 8 rho pi square v cube in its omega square, limits of integration from 0 to omega d. So we'll solve this limit of integration and we get omega d square minus 0 square, which is actually nothing, and 3h cut omega d square over 8 rho pi square v cube. This is something that we had to prove at first place, and yes, we have proved it, that the mean square lattice displacement at absolute 0 is given by this expression, as we successfully solved the expression that was given to us to start with, and we began the calculation by that formula, and we proceeded, and we successfully proved that the mean square displacement at absolute 0 is equals to this expression under Debye approximation. All right, now let us see what happens when we consider this formula of mean square displacement for a 1D lattice. Okay, and for this we'll use this formula, equation 2 again. Here the 1D lattice will be implemented on this formula by means of the density of states. We'll put the formula of density of states in 1D into this expression, and we'll solve it, and we'll see how it doesn't converges and diverges. And yes, so we have for part B. Okay, this is part B that started. Mean square displacement in equation number 2 is h cut over 2 rho v 0 to omega d 1 over omega d of omega d omega. So I'm writing it again. So let me tell you, the value of d of omega for 1D lattice is equals to L over pi v. Okay. So this is the density of states in omega space, which you can simply convert, as you know that the density of states for 1D system in K space is actually L by pi, and you can simply convert it by using the similar procedure that I used previously for the 3D one. Okay, so it's L by pi v, and all of these quantities are constant. L by pi v and 0 to omega d 1 of omega d omega is h cut 2 rho v L by pi v, and if you integrate 1 over from omega, you will get natural log of omega as the integration of you can easily see that the integration of 1 over x for dx is natural log of x. So this is the similar case, and if you put the limit of integration right into this integration, then you will get this expression, and this expression tends to be infinity. Okay, this is not defined, so the integral tends to diverge for a 1D lattice. Hence, summation 1 over omega and resultantly diverges for a 1D lattice. Alright, this is proved now, and let us do the other proofs now, which are for, let's talk about the part B, where we have to prove that the mean square strain as given by this formula. We have to start with this formula for mean square strain, and we have to solve it to prove that it is equals to this expression for a line of n atoms. Okay, we have a one-dimensional case here because the line of n atoms has been shown in the statement, so it will be a 1D case obviously, and each of mass capital M, all of the atoms have a mass equal to m, means each atom, for example, this atom is of mass m. All of the atoms individually are of mass m, and there are capital N atoms. Here, counting longitudinal modes only, we have to consider the longitudinal mode only. None of the other modes will be considered here. So we'll take the expression of density of states for a single mode only. Okay. There are the other words that are used instead of modes, which is like polarization. Okay. So if polarization words comes here or a mode word comes here, so they refer to a similar thing. Okay, that there are actually three modes of vibration, two transfers, and one is longitudinal. Okay, so or you can say the word polarization instead of modes. So let's solve this problem, and we know that we can say we are given with the mean square strain expression as to be like that. Okay, k square u naught square. Here u naught is the amplitude of vibration, k is the k vector. Okay, as we already know. Now let's expand that summation into an integration, as we know that it will run from 0 to kd because k is a variable here. Okay, in previous case the omega was the main variable, but here k is the main variable, so it will run from 0 to kd. Kd is the Debye wave vector. Okay, the maximum wave vector that the atoms could have, and k square u naught square, this is the main function multiplied by the weight function, which is density of states in k space, because the integral is in k space. So you'll choose the space accordingly. K square. Now u naught square is the amplitude of vibration of atoms, and we have to insert some value instead of u naught square here, so that our integral gets solved easily. And for that one purpose, let me write it as it is, like right here, and we'll put its value after putting the value of d of k right there. And we know that for a 1D case, since there is a line of n atoms, line means a 1D case, so for a one-dimensional case the density of states is equals to L by pi. Okay, the density of states equals L by pi in K space. Okay, in omega space it is equals to L over pi v. Okay, so which space you are considering should be the first noticing thing for you before putting the values. Alright, so it is in K space, so I'm putting the value of density of states in K space and dk as it is. Alright, now we need to find out the value of u naught square and plug it right here before actually integrating the whole expression. And let us call this equation as equation number 4. Okay, so, and keep that in mind, we are considering everything in 0 point. 0 point is the point of minimum energy, minimum temperature. Okay, so we know that the 0 point energy of harmonic atoms is, okay, atoms are behaving as a harmonic oscillator. This system of atoms are behaving as a harmonic oscillator, so their energy is equals to we know this expression 1 over 2 mv square. Okay, and we are considering here the total energy. Keep that in mind too. So 1 over 2 mv square is the general expression, and know that in angular variables v is equals to r omega. And if you want to consider insert here the amplitude of vibration, v is the speed here, omega is the angular frequency, r is the displacement from mean position. If you want to insert here the u naught expression, it will become like that. Okay, because our data is in u naught form, so we'll plug the value of speed, this one, okay, where m is the total mass of the system, 1 over 2 total mass of the system. We have a system of n atoms, each of mass capital M, so the total mass of the system will be capital N times capital M. Okay, so we'll put capital N, capital M in place of the small m. Okay, and u naught square omega square is the energy. If you put it square, so we have 1 over 2 capital N m u naught square omega square, okay, as one of the form of energy of a harmonic oscillator, and that would be equals to h cut omega. Now let me give you some. For a 1D oscillator, this is the general expression for its energy. Okay, in quantum mechanics you are familiar with this form of energy for a harmonic oscillator in one dimension. Okay, this 1 by 2 expression shows it, and one single n shows this fact too, that it is for one dimension, because in 3 dimension the expression took the following form, something like that. Okay, so that's not relevant here, I'm roughly writing it, maybe don't take this as the main thing. So this is for one dimensional harmonic oscillators energy, and for 0 point energy we'll put n equal to 0, so we'll get 0 plus 1 by 2, which is 1 by 2, and h cut by omega by 2 is the energy of a harmonic oscillator in its 0 point, okay, ground state energy. So this 2 and 2 gets cancelled out in both direction on both side of the equation, and we are left with this expression. Okay, 1 omega cancels out, we need the value of u naught square, so u naught square here, h cut by capital N m, and 1 omega right here, and we want the expression in k space, not in omega space, and for that purpose, using the Debye approximation, where we know that the this expression holds. Okay, we can find out the value of omega here by taking k on that side of equation. So we get this as the value of omega. We'll put it right here, v k. Okay, so let us plug this value right into the equation 4. So the equation 4 was partial r by partial x whole square mean, this is strain, this is square, and this is mean square strain, that is equals to 1/2 0 to kd k square and u naught square here, L by pi from density of states expression, and dk here, 1/2 0 to kd k square, and we'll put the value of u naught square, which was n capital M v k, L by pi dk, and this k and cancels out. Okay, and rest of all the values instead of k. Okay, keeping k values aside, all of the other values are constant, so they will come out of the integral, and h cut L, our capital N M v and pi are the values that are constant, and they will come out of the integral, and integral on k v, this is v speed. Okay, and it gives k square by 2 as the integration of this integral, and h cut L, this 2 gets multiplied with this 2, which becomes 4 pi capital N M v, and putting the limits kd square minus 0 square, which is again 0, so we are left with this expression h cut L kd square over 4 pi and capital M v, that is equals to partial r by partial x. Now the expression that we want to prove has the omega as the main variable, so we have to convert this expression in k variable to omega variable. So for this, we know this expression v is equals to omega by k, so v equals omega d by k d2. Okay, for all values of omega and k, the ratio will be a constant, which will be equals to the speed of sound in Debye approximation. So whether it is omega 1 by k1, omega 2 by k2, omega d by kd, the ratio will always be equal to the speed of sound. So we can use this one expression, and kd hence would be equal to omega d by v. Simply we'll put the value of kd right into here, square means this. Okay, so let us put this value right here, and omega d square by v square, and h cut L omega d square by 4 pi capital N M v cube, this is speed and this is speed too, so v cube, and this is the expression, final expression that we wanted to prove. Okay, and this is the mean square strain, and this is the final expression that we wanted to prove too. Now in problem statement, pi is not in the denominator. There is a mistake in the question, because I have done that problem multiple times, and every time I get pi, and there is no other way that the pi gets eradicated from the equation. So there is a mistake in the question statement. There is a additional pi in the denominator. Okay, and this is something that we wanted to prove at first place. We can see here that the mean square strain is finite for a 1D case at absolute 0, and that is equals to this expression, as we can see. Okay, though the mean square displacement diverges for a 1D lattice at absolute 0, but the mean square strain is finite. Is also mentioned in the question statement that the r square diverges. That thing doesn't affect or holds the significance in physical measurements. Okay, that doesn't matter. I hope you all understood the problem, and like, share and subscribe. Goodbye, take care.